Bismillahirrahmanirrahim. Assalamu alaikum everyone. Today we are going to conduct the second lecture of this online session series. The topic of this lecture is memory organization. In last lecture we concluded the software model of 8086 or 8088 microprocessor. Let's re-examine some of the facts that we learned in the last lecture. 8086 microprocessor has 1 million locations in its external memory, while each of these locations can store 1 byte of information. Thus, the total size of this memory is 1 megabyte. Each of these locations have very unique addresses which ranges from 000 hex to FFFFH hex, or 5 times zeros in hexadecimal to the 5 times F in hexadecimal. This number of locations as 1 million was calculated by raising the number of bits present in an address to the power of 2. Since we know that the address was 20-bit long, so 2 power 20 will become 1 million byte. We have done the same calculation in the last lecture. If any one of you have some confusion, you can clear by reviewing that particular lecture. Memory is present outside the microprocessor, and it is not the physical part of the microprocessor, since to function the microprocessor it requires memory. So that's 1 megabyte memory which is available for 8086 or 8088 microprocessor within that software model. Programmer must assume this memory to be used as storage place for programming code. With this point, we are going to review another important aspect of memory that we discussed earlier, in earlier lecture before this online sessions. The aspect, and that particular aspect was these Intel's microprocessor were based upon the von Neumann architecture. And what is that von Neumann architecture? Just to recall it, von Neumann architecture refers to the microcomputer architecture in which program memory and data memory are implemented within the same chip, or in other words, program shares data to be manipulated within the program, and the program itself shared the same memory chip. 8086 or 8088 microprocessor is a 16-bit microprocessor. That means only 16-bit of information can be processed by the processor in one machine cycle, or in simple words, only 2 bytes of information can be processed at once. Now let's try to look at the same fact from the memory point of view. Let's consider this small chunk of 8086 or 8088 microprocessor's memory. We see the two columns here. The left side column, this one, this left side column indicate the address of the location, while the right side column indicate the content stored within those locations. And this is the 16-bit processor which is about to access the information from the stored memory, which is shown here. What do you think? How many bytes of information will be accessing if the processor is trying to access single location? Of course, it will be only 1 byte of information. We can see here. This is only 1 byte of information. So if processor is trying to access only single location, that means only 1 byte of information will be coming. Will it be useful for a 16-bit processor? No, definitely not. Because we are going to force, and if we are going to force to do the same thing for this processor, then we are not using this processor up to its optimum efficiency. So rather, accessing just one location is going to fetch two consecutive bytes or 2 bytes of information from the two consecutive locations. You can see that only these two locations are being fetched by this microprocessor. So this is how microprocessor is trying to access this is how microprocessor access 2 bytes of location or two locations at the same time, and each of those locations have 1 byte of information. So in total there are 2 bytes of information which is being accessed in every machine cycle by this microprocessor. So if we summarize the whole stuff, 8086 or 8088 microprocessor access 2 bytes simultaneously, and these 2 bytes commonly known as a word. So out of those bytes, which one will serve as a least significant byte and which one will be treated as most significant byte? Answer to this question is the little Endian approach. I'm not going to discuss this approach in detail as I have explained it in the class lectures in quite detail. So I will try to suggest you to go through the classwork and Google it and not to note it down, so as it will be part of your assignment as well. So by using the little Endian approach, the lower address byte will be treated as the least significant byte, and a higher address byte will be treated as the most significant byte. We are going to take another example of this. Let's consider an example in which we can see that there are two memory locations, and each of them has certain content. This is the first memory location, whose address is 7208 hex and the content is 72 hex. This is another memory location and its address is 07207 hex and the content is 4B hex. We can clearly see that this is the lower addressed memory location, and this one is higher address memory location. So word is being fetched from these two memory locations. So what will be the word to be fetched? So by applying the little Endian approach, the least significant byte will be 4B because it is stored at lower address, which is 07207 hex, and the higher significant byte or the most significant byte is 72 hex, which is stored at 07208 hex. So the word which will be fetched from these two memory locations will be 724B hex, and since all of these are shown in hertz, so if you convert each of them into binary, you will see that these are basically 16 bits of information. Now we are ready to get introduced with two important terminologies of memory organization, and those are even address boundary and odd address boundary. These are basically locations at which different data types are stored. Let's learn about them one by one. Even address boundary. These terms are based upon the address of memory locations from which information is being fetched. if the address of the least significant location is even, then the location itself is known as even address boundary. How one can identify the address is even or the odd? In binary, it's quite easy, and one can easily identify just by inspecting the last bit of an address. If the last bit of an address is 0, then it will be considered as even address. And if the last bit of that address is basically 1, then it will be considered, or the address will be considered as odd. So if the least significant bit of address is 0, then of course we are talking about even address boundary. Furthermore, the information which can be of any type, byte, word, or the pointer, which we are going to examine in the coming lectures as well. So the information stored at the locations which have even addresses are known as even address boundary information, and they are basically corresponds to two consecutive information. We do not look for the highest significant byte, we look for least significant byte. And this concept will be much clearer when we are going to take an example. Just to just to provide you a simplified example, we have uh, least significant bytes. If the least significant byte of the word which is being fetched is stored on these locations 000, 724 or 000 or 004 or any multiple of 2, they are definitely even address boundaries, and they are also known as aligned words. What is and it's a new concept compared to the even address boundary or the odd address boundary. When we talk about boundaries, we are referring towards addresses, while when we talk about the information which are stored on those particular locations, we refer them as aligned or misaligned word. For misaligned word, we are going to see them in the next slide, but in this slide we are just explaining aligned words. So if I summarize all the stuff, if the address of the location is even, then the location will itself will be termed as even address boundary. And how one can identify it is even or odd? We have to see if it is in the binary, we have to see to the last bit of the address. If that address is 0, then it is even address. And if we are talking about in hexadecimal, like in these examples which are given in the third point of this slide, we have to look for the multiple of the 2, and if those are basically multiple of 2, then we are talking about even address boundary locations. And that is just about the boundary locations or the location itself. What is the content? So if the location is even boundary, then the content stored in that particular location is known as aligned word. We are going to further exemplify these things in coming slides. Well, in this slide we are going to discuss about odd address boundary, and it's totally opposite what we learned about even address boundary. In odd address boundary, it's a type of the location at which the different information or different type of information is stored. Well, if the address is even, then the location is known as odd address, so even address boundary. And if the address is odd, then the location is known as, or the location where information is stored is known as odd address boundary. And how one can identify that whether this particular location is even or odd? It's the principle is same as we discussed in the last slide. If you are seeing the address in the binary, you have to look for the last bit of an address, and if that last bit of the address is odd, then we are considering that particular location as odd address boundary. Furthermore, as we know that microprocessor fetch not just one single byte, rather it fetches 2 bytes of information or a complete word. So how we are going to identify whether the word is coming from an odd address boundary or an even address boundary. It depends upon the least significant bytes address. If the least significant byte of the word is coming from an odd address, then we termed that particular boundary as even address, sorry, odd address boundary. Or if the least significant byte of that word is stored at even address, then we term the whole boundary as even address boundary. Further, if we are going to take an example, I'm again trying to mention some of the uh, odd addresses in hexadecimal, and one can easily say or identify these are basically not the multiple of 2, which means they are definitely odd numbers in hexadecimal. So, and again the concept comes to the misaligned things, and it's again about the information stored inside the location. I'm going to summarize the same thing that I explained in the last slide. If we want to classify the locations where information is stored, we see and we inspect for the least significant byte address, and if we see that that address is odd, then we classify those particular locations, those two locations. Of course, we are talking about two locations because we are going to fetch two different bytes from two different locations. So those two locations will known as odd address boundary, since their addresses are odd. But what about the content which is stored inside those locations? The information is known as misaligned words. And this misaligned or aligned concept doesn't stick only with the words. It can be actually exceeded towards different data types, and we are going to learn in coming lectures. Well, in this slide, we are going to learn these concepts in further detail. Here we are going to take an example. Uh, Here in this example, we show the two different locations which are from 8086 or 8088 memory. This part, let me highlight them. This area is basically address. This area is information which is stored inside the memory, and this area is again information stored inside the memory but in hexadecimal. One can clearly see that it is 0101, which means 5 in hexadecimal, 50101, which means 5 in hexadecimal. Similarly 000, so it basically 0 in hexadecimal. The 0010 is 2 in hexadecimal. So these are two locations, so definitely a word is coming from these two locations. But the question is, which one of these two locations will be considered as lowest significant byte, and which one is considered as the most significant byte? And the answer to that question is basically Little Endian approach. In Little Endian approach, the lower byte of information is stored at lower address, and the higher byte of information is stored at the higher address. Which one of them is lower address? This one. Look, 00724 it is definitely less than 00725 hex, and the content of 00724 is 02, and the content of 00725 is 55 hex, which means 02 will serve as a low significant part of the byte or the word, and 55 hex will be the most significant byte of that particular word. Now question arises, is it aligned or misaligned? How we can solve this example? This is quite easy. First of all, we have to look for the least significant byte, and we come to know that 02 is the least significant byte. Where it is stored? It is stored at 00724 hex. 00724 hex. Is it even or odd? It's even. Yes, because it is a multiple of 2. Further, if you want to check it, you can further convert it into binary, and you go and check the last bit of the address, you will find it will be 0. What is the last hexadecimal number here? It is 4. So what is the binary combination for 4? It's 0100. That means 0, the last bit is 0. So it is confirming that this is even address, and its least significant byte is stored as even address. So this means that least significant byte address is 00724, and its value is 02 hex, and it is even address boundary because the least significant byte is stored at even address, while the most significant byte, of course the next byte is going to be a most significant because it is stored at the higher address as well, and that is 55. So complete word will be least significant byte is 02 hex, most significant byte is 55 hex, so complete word will be 5502 hex. And the thing which is to be noted here, it is going to be what it is going to be. It is going to be an aligned word. Why it is aligned word? Because it is stored at even address boundary. I hope you have understand the concept. So in this slide we are going to extend our knowledge, and we are going to explain them with different example, and this example is again taken from your book, from your textbook, and we are going to uh, check for different bytes and different words. We are going to inspect whether these words are aligned or misaligned. So before we go in further detail, I want to just explain it for the startup procedure. This area is basically this area. Let me highlight it for you. This is an address part. This one is your actual physical memory, which means the original information stored inside this memory. We haven't used here any kind of exact information like in binary or in hexadecimal, but we have just named that whatever that information, it is equal to 1 byte, and this is your byte number 0. Let me use the marker. Okay, that this is your byte number 1, this is your byte number 2, byte number 3, and so on. And furthermore, if you combine these two words or these two bytes of them in one word, so it is equal to one word. Like here, byte 0 and byte 1 is actually forming a word which is equal to word 0. Similarly, byte 3 and byte 2 are combining and creating word 2. Similarly, byte 4 and 5 are combining and creating this word 4, and so on. So let's inspect a random word and check whether it is even or odd. Let's first try to, let me clear the whole stuff so that it will become more easy for us to understand. So let's consider this word number 6. How we are going to examine? Let me use a pen. Okay, we are going to check this word 6, and word 6 is basically composition of byte 6 and byte 7. So this word number 6 is basically composition of byte 6 and 7. So how we are going to determine which of these two bytes is least significant? The least significant byte is this one, byte number 6. How can I tell it? Because byte 6 is stored at 006, while most significant byte is byte 7 and it is stored at 007. Why? Because using the Little Endian approach, we know that lower or least significant byte is stored at the lower address. Which one of them is lower address? Lower address is this one, 0006. So the low address is basically 006, so it is the least significant byte. So byte number 6 is uh, least significant byte, and higher address is 007, so most significant byte is byte 7. So is it a aligned word or misaligned word? It is aligned word. Why? Because the least significant byte is stored at the even address boundary. See, so 06 is its even address. That means word 6 is aligned. Now let's take another example to clarify this concept again. First, let me remove the stuff so that it becomes more easy. Let's take example of these two words, these two bytes, byte 3 and byte. Okay, this is not given in that example, but we can consider it. Okay, byte 3 and byte 4. So which one of them is least significant? Because byte 3 is stored at 03, byte 4 is stored at 04. So byte 3 is stored at lower address, so byte 3 is our least significant byte. And since byte 3 is our least significant byte, which means this complete word gonna fall in the category of misaligned words. Why? Because byte 3 is the least significant byte, since it is stored at the lower address, and this lower address is what? Odd address. So that means it is an odd address boundary, and whenever the information is stored at the odd address boundary, the complete word goes to the misaligned word. I hope you understand the concept. Well, let's take another example. This time we're gonna take from this specific example. Let's talk about word 1. This word 1 is basically composition of byte 2 and byte 1. So which one of them is basically least significant? Byte 1 is least significant. Why? Because it is stored at 001, and 001 is lower address compared to the 002 hex. So byte 1 is least significant. Now we have to check the byte 1 is stored at even address or odd address, and byte 1 address is 001, and it is your odd address. That means this complete word gonna fail in the category of misaligned words, and we can see that misaligned word is shown here. Word 1 is misaligned word. Let's take one more example. I hope it will be clear then. Let's take an example of let's say word 4. That word 4 is composition of byte 5 and byte 4. So which one of them is lower address or least significant byte? And this one is basically lower address. Let me use another color. Sorry, that's not good color to highlight. Yeah. So byte 4 is stored at 004, while byte 5 is stored at 005. So which one of them is basically lower address? This one is lower address, byte 4, and byte 4 is least significant byte. So least significant byte is stored at even address. 004 is definitely is an even address. So byte 4 and byte 5 combinedly known as word 4, and it is going to go towards aligned words because it is even address boundary. I hope I have cleared the complete concept of even address and odd address boundary. In this slide we are going to examine another example of data type, and that is other than the word, and it is double word. What is double word? Double word is 4 bytes of information, or the composition. It is composition of two different words. Uh, like the word was formation of 2 bytes, 16 bits. Similarly, double word is combination of two words or 32 bits. And the common example is pointer. Pointer is a word which refers to the memory location where 4 bytes of information can be stored. It can be any memory. It can be data memory or code memory. It doesn't matter here. So it's another uh, reformation of the words for the same thing. Double word is another data form that can be processed by 8086 or 88 microprocessor. So double word, pointer, two word is the same thing. Same thing corresponds to 4 consecutive binary location. We're gonna take an example of this as well in the coming slide. Well, it is interesting. It is quite interesting. In this example, we are going to consider the same kind of example that we described in case of words, simple words, but here we are going to deal with pointers or the double word. Let's take, first of all, let me set the starting procedure. That is your address, and this is your physical memory. Again, we are using just random words: byte 0, byte 1, byte 2, byte 3, byte 4, byte 5, and so on. So, in case of double word, we need to consider 4 different locations. We can't consider 2 bytes. We have to consider 4 different bytes. So, let's consider we are talking about this word. These are basically how many bytes? 4 bytes. So we have to answer the same question whether this double word is aligned or misaligned. How we are going to examine? We have to go to least significant byte. And which one of them is least significant byte? This one. This one is least significant byte because it is stored at the lowest address. Yes. And what is that address? Is it odd or even? It's definitely odd, 003 hex. So it is going to be misaligned double word. The full thing is going to be, this complete word is going to class of misaligned double words. Yes, this double word is misaligned because the least significant byte is byte number 3 and it is stored at 003 hex. Let's consider another example. Let me rub it all of them. Okay, let's consider this double word, sorry, this byte 1, byte 2 and byte 3. These are again 4 different locations. So which one of them least significant byte? It is byte number 1 because it is stored at 001. So is it going towards aligned or misaligned words? It is going towards misaligned word because it is again the least significant byte is stored at 001 hex, which is odd address. That means uh, this word, sorry, this double word is going to misaligned words because it is odd address boundary. Let's take another example, and this time we're gonna take another example of, let's say, aligned words. Let's talk about this word. Let me highlight it for you. This one, byte 4, byte 5, byte 6. Is it double word? Yes, these are 4 memory locations, so these are basically double word. 4 different bytes or 32 bits of information. The lowest byte is byte 4. Where it is stored? It is stored at 004 hex. Is it even or odd? It is even. So the this complete double word, it is aligned and it's going to category of aligned words. I hope I have explained this full concept of misaligned and aligned word in great detail now. I hope you have understand the concept. Let's take an exercise problem, and here we are going to see another memory section. This is the memory section we have considered in this exercise problem. Uh, this part is address, this part is the content of information. So question is, find out the data word which is stored at B00 hex. First of all, we have to find out this location, and that's here, B003 hex. And what is the value of this location? The value is 55 FF hex. And what is going to the next byte of this word? It is going to be the next location, this location, then that is B001 hex, and its information is 00 hex. So the now question is that which one is the least significant byte? The lower address is going to be least significant, and the higher address is going to be higher significant. So least significant address is least significant byte is FF, this one, and higher significant byte is 00. So the word is 00FFX. I've just arranged them in the right order. Higher comes first, lower comes later on. So whether it is aligned or misaligned, it's definitely going to be aligned, because the least significant byte FF is stored at even address, which is B00. So that is going to be our even address boundary, and the word is going to be aligned. Well, in this slide, we are going to take another exercise problem, and this time we are going to discuss the double word. It's again same thing, same memory chip, but we have considered a different exercise problem. That column is basically address, this column is the data content. So what is the question? It says find the value of double word starting from the location B003 hex. Where is B033 hex? It's here. That is B033 hex. So we are talking about double word, which means 4 byte of information. So that's our first byte, that's our second byte, that's our third byte, and that is our fourth byte. So the double word will be 44332211. Okay. Well, the next question, is it aligned or misaligned? We have to go to the least significant byte, and which one is first of all, let me remove it. So the least significant byte is this one, because it is the starting address or the lower address, right? And its address is B003 hex, which is odd or even. It is odd, so it is going to be misaligned double word. I hope I have explained every aspect of aligned and misaligned, the concept and the related terminologies. And here we conclude our this session of this online session lecture series. If you have any kind of questions or any confusions, note them down, and we will try to discuss them during our online session of team. Well, thank you so much for listening. That's the end of the lecture.